7.2, techniques for solving exponential equations. So yesterday we were working with exponential equations and we learned a change of base strategy, and then we could solve equations using that change of base strategy. Today we're going to have another strategy or two, and it gets a little bit more complicated, but I think it'll be okay. Straight into example one. Example one is the concept, uses the concept of half-life. Do you know what half-life is?
Yeah, we all went actually in chemistry. It is how long it takes for an unstable thing to decay.
By half. Good. So the time taken for some material, some chemical, something to decay to half its original amount. Good.
We already looked at this in functions, so.
Exponential equations have a lot to do with this, and now we're looking at it as a decay. Okay, here we go. Polonium-218 is a radioactive substance that spontaneously decays into lead-214. 1 minute after a 100 milligram sample of polynomial 218 is placed into a nuclear chamber, only 80 milligrams will remain. So this time we are not given the half-life. We have to figure out what the half-life is. So what we're going to do is use our equation for half-life, which is the amount with respect to t, the amount after a certain amount of time, is equal to the original amount, A naught, times 1/2 to the power of t over h. In this formula, A is the amount, t is time, A naught is the initial amount. Maybe I'll draw little arrows to certain things that we're just maybe learning about or remembering. Initial amount. H is the half-life measured in years. And T is the years, so T here and T there. T is time in years. And of course, we're multiplying by 1/2 each time to indicate that it is half-life. The amount gets cut in half every time we experience a full half-life period. But this form of it with the T over H in the exponent allows us to use this for partial half-life periods as well, which is helpful in this case because we're going from 100 milligrams to 80 milligrams, not down all the way to 50 milligrams. So with the scenario that we're in, let's just list the things that we know. Thanks for that. We know the original amount is 100 milligrams. That's A naught, the initial amount. We know that T is given as 1. And we are told the amount that remains after 1 minute. So A sub T, or in this case A of 1, is 80. So we're going to take all of that and sub it into our equation. So A, the amount remaining that we're looking for, A of T, which is A of 1, because we're interested in what's happening here after 1 minute. 80 is equal to the original amount, which we also have, times 1/2 over T to the power of T over H. I'm just trying to connect why I have it measured in years. Okay, sorry, so time in years and in years. So these are the same unit of measurement. They're both measured time in years, okay? Basically, you just need to be using the same unit in the t and the h. So in our scenario, we're actually working in minutes. So I'm going to have 1 over h, which when we solve for h is going to express the half-life period in terms of minutes.
Yeah.
Okay? Carrying on, what do we do first? Starts with basic algebra. What's the easiest thing I'm going to do? I'm trying to figure out what h is.
Well, you can factor. Actually, no, you can't. Can you factor 100 out of both sides?
I can divide both sides by 100.
Okay.
Okay, on the right, that leaves me with 80 over 100, which is on the left, 0.8. And on the right, we now have 1/2 to the power of 1 over h. Now what? My variable is in my exponent.
Well, we can use a logarithm thing.
Yeah, I'm gonna, what do we say that? We take the common log of both sides.
1 over h is equal to a logarithm of 0.8 to the base of 1/2.
Let's work through it step by step. So far we've taken the log of both sides. Now what? Which rule can we apply? I'm sure you know what to do, you just don't know what it's called. Apply the power law of logarithms. Power law of logarithms says that you can take the exponent here and put it as a multiplier out front. So the left side doesn't change. We still have log of 0.8. But on the right side, we now have 1 over h times the log of 1/2. And at this point, and even earlier, I could have done this, but if we're using decimals on the left, we may as well use decimals on the right. 0.8 and 0.5. Well, my goal is still to solve for h. Right now I have h in the denominator. So what am I going to do next?
You can just get the log of both now.
You can, but then if you got the log of both now, then you'd be inserting a rounded number into the equation, and then you'd be using that rounded number in further calculations, which would give you a greater room for error.
1 over h equals log 0.8 over log 0.5.
Yeah, I could divide both sides by log of 0.5,
Yeah.
and then take the reciprocal of both sides. Could do that.
Oh, yeah, we could do that. I didn't think of that.
Let's do that. Divide both sides by the log of 0.5, which would get us, I'm going to put my 1 over h on the left now. We have the log of 0.8 over the log of 0.5. Now you can take the reciprocal of both sides, which gives you on the left just h over 1, which is h, and on the right you get the log of 0.5 over the log of 0.8, which is, in your calculator, it's approximately 3.1. Okay, so h is 3.1. In this case, that means the half-life of polonium-218 is approximately 3.1 minutes. Okay, so the half-life of, I'm just going to call it P-218, is approximately 3.1 minutes. Just quickly, the other way to do this is you would actually multiply both from this step. You would multiply both sides by h and then divide by this fraction, which is the same as multiplying 1 by the reciprocal of this fraction. So it ends up being the same. But you'd multiply both sides by h and go from there. Sorry, you could do that even here. This is where you would do that. You'd multiply both sides by h. You'd get h log of 0, h times the log of 0.8 equals the log of 0.5, and then you divide both sides by the log of 0.8. So you'd end up with that. Okay. So whichever way you want to do it is fine. Now we want to graph the decay function for polynomial 218. To graph it, we basically would, now we have our basic formula. So if we just, maybe you have room underneath yet, or just off to the bottom right or wherever, but I'm going to go up here for B. For graphing it, we need a function. We need a function to graph. So let's take our function up here and sub in what we know for this specific case. We're not going to do it at a specific time because that would be solving. That's what we did originally in order to determine the half-life period. But now that we know the half-life period, we can say our original amount is 100. Its half-life, so our fraction that we're multiplying over against is 1/2. And we don't know what t is. That's the nature of a function. That's our independent variable. But we do know that h is 3.1. Okay, so this is what the function would look like here. And you just punch that into Desmos or into a graphing calculator, and it will graph you something that looks like this. Where do you think it crosses the y-axis? I'll give you a hint. It's the amount that you started with. Yeah, 100. And if you wanted to give it a bit more precision, you already know that after 1 second, it's at about 80. You don't need to add these numbers necessarily, but this is approximately what it would look like. Good. Quick review. Start with the formula for half-life. Sub in what you know. Use logs and exponents to answer the question. That'll give you the half-life period. Then you can go back into the general equation specific for polonium 218, in this case with a half-life of 3.1 minutes, and we started with 100 milligrams. Okay, solve the equation. 4 to the power of 2x minus 1 equals 3 to the power of x plus 2. Example 2, what seems to be the difficulty here? What's going to be challenging for us here? What looks like it could be challenging for us here? If this were a 2, what would we do? We'd express this 4 as 2 to the power of 2, right? And then we'd expand the 2 in here. We'd have power of powers, and then we'd have the same base, which means we could equate the exponents.
Well, I could do a common, like, multiples,
Common multiples?
like 12 and 12.
So you could multiply this base by 3 and this base by 4?
Yeah, instead of dividing.
Or would that be doing something different to each side? And also, it's not 4. It's 4 to the power of this thing. So that gets a bit dicey.
How did we do it with, like, 2s and 8s that was allowed?
So basically we had, if I just erase this 3 for a second and we put a 2 there, we could have expressed this as 2 to the power of 2,
Oh yeah.
in which case this would be 4x minus 2. And since they have the same base, we would just say 4x minus 2 is the same as x plus 2, and then solve from there.
Okay.
Okay? That is not going to work in this case because we have these bases that don't have anything in common. One isn't a power of the other one. But we're going to go back to our tried and true strategy that when I'm working with exponents and I don't know what to do, I'm just going to take the common log of both sides. Yeah? Step number 1. Common log both sides. So right away, that should start coming to your mind, because what it allows you to do is it's going to allow you to take the exponent out of the exponent every time. So you take the log of 4 to the power of 2x minus 1. That is equal to the log of 3 to the power of x plus 2. The next step then we know is to apply the power law of logarithms, which allows me to bring this 2x minus 1 out in front of the log of 4, and x plus 2 out in front of the log of 3. Okay, now from here I can understand you might get a little bit stuck. Basically, you're working with two different things. Your goal is to solve for x, but right now you've got an x in a bracket and multiplied by a log of 3. And over here you've got x in a bracket and multiplied by log of 4. It's kind of like, how do I separate all of this into its bits and pieces? If you are left with a binomial and another value, what could you do? What is a mathematical possibility?
Well, you can divide. Maybe can you divide x plus 2 from the other side?
I could divide both sides by x plus 2, or divide both sides by 2x minus 1, but all that's going to do is put my variable, now I'm going to have one in the numerator and one in the denominator. I don't really want that. Is there another?
But you have all your x's on one side.
Yes, but if one's in the numerator and one's in the denominator, the only way to get it out of the denominator is to multiply both sides again by that value. So that would be working backwards. But you're right, that is mathematically, that is something that we could do. So let's eliminate that option. What else could you do? How else could I express this? And what's it called when you do that? Starts with a D. DI. DIS. DIST. DISTR.
I can't think of any words.
I've taught you nothing.
You're spelling out distraction. Oh, distribution. Let's see.
All right. So if we distribute over here, we're going to make it longer and uglier, but after that we're going to be able to isolate x. The only way to get these x's together is to unpack both of these sides. Okay? So we're going to distribute on the left and on the right. Here we go. On the left we have 2x times the log of 4 minus the log of 4. On the right we have x times the log of 3 plus 2 times the log of 3. Now we can bring our x's together. So I'm going to subtract.
Well, they're on two different logs.
Yep, they are still, so that's another step coming up. We're going to subtract. Remember, the log of 3 is just a value. It's just a certain number of x's, which is fine. It's an awkward number, and we don't want to approximate it. We want to keep it as an exact value, but it really is just a number. It's like having 1x or 2x or 3x's. You have log 3x's. Okay, so we're going to subtract that from both sides, and at the same time I'm going to add the log of 4 to both sides. So on the left here we have 2x times the log of 4 minus x times the log of 3, and on the right we're going to have 2 log 3 plus the log of 4. This is collect terms with a variable. All right, so
This is going to end up on the test.
you're right. We still don't really like that we have this x attached to log 3 and these x's attached to log 4. Can you think of any way that I can kind of disassociate the x from directly being attached to this term and that term?
Well, log 4, you can just say is 1000 because it's log 10 to the 4. You can do the same thing for log 3.
It's not though. So it's not 10 to the power of 4, it's 10 to the power of something that will make that equal 4.
Oh, yeah.
So it's the exponent that's missing, actually. Yeah. So what can we do? These terms both have an x. Factor out x on the left. Okay, so if I factor out x from each of these, that puts x outside of a bracket. Inside the bracket, I have 2 log 4 minus log 3. On the right, we haven't changed anything. 2 times the log of 3 plus the log of 4. Now, it still looks really awkward, but look what we've done. X is by itself. And everything in this bracket is actually just numbers. There's nothing missing here. These are just numerical values. So now what we can do is solve by dividing both sides by that binomial there. So I divide both sides by 2 log 4 minus the log of 3. And in the numerator on the right, I have 2 times the log of 3 plus the log of 4. That comes directly from the right side. And this, again, it looks awkward, but it's really just values and numbers, okay? And you can type that whole thing in one go in your calculator if you do it carefully. I'll give you the answer, and then we'll go ahead and try that a couple times to see if we can get the same thing. But if you do it carefully, you should get 2.14. So, quick recap. Take the common log of both sides. That's the thing that's new. The rest of it is algebra skills that you already have. Distribute, isolate the variable, factor it out. These are just values. Value has a number, it's an exact number. It just looks awkward, and then divide it out on both sides and solve. In the next example, it's kind of similar in that you use some new skills, some old skills, but it's a little trickier to see right off the bat. So I'm just going to write it down here, and then we'll talk about it for a second. We've got 2 to the power of x minus 2 to the power of negative x equals 4. Notice we have base 2 here raised to the power of x and base 2 raised to the power of negative x. Now, what power of 2 might fall in between these two? Like if I was making a list of the powers of 2 and I had 2 to the power of x and 2 to the power of negative x, what might go in between there? What am I missing?
X to the 0, 2 to the 0, which is 1.
2 to the power of 0, which is 1. So think with me for a second. We have a term that is 2 to the power of x. We have a term that is 2 to the power of negative x. And we actually have a term that is 2 to the power of 0. We have 3 terms that are descending powers of 2. Does that strike you as anything familiar that you've learned about in the past? Possibly. Maybe something that looks a little bit like this. Yeah?
Yeah, but we don't really know what order.
Ax squared plus bx plus c, except we don't have it. We have powers, x is the exponent, but we've got 1x and negative 1x and 0 x's. Anyway, that's what you're supposed to see. This should make you look, it should kind of look like a quadratic equation. So that's our goal, is to notice this has some similarities to a quadratic equation. And to help it look like that, what we're actually going to do is multiply both sides by 2 to the power of x to help us along. Multiply both sides by 2 to the power of x. Okay, so let's see what happens if I do that. I'm going to do it in a couple of steps. We're not going to rush it, but I've got 2 to the power of x times this left side. And I've got 2 to the power of x times this right side. And now I'm going to distribute and simplify. So here I have 2 to the power of x times 2 to the power of x. Just going to I'm writing every step. Okay, you probably already know with your your product law of powers, but I'm going to write every step. 2 to the power of x times 2 to the power of x. I also have 2 to the power of x times 2 to the power of negative x. And on the right, we're not going to touch that yet. Now applying the product rule for exponents, if I am multiplying two powers with the same base, what can I do to their exponents?
And add them.
I can add them. So I actually have 2x, 2 to the power of 2x. Here we can say what we've done so far. Distributive property and product law. Here we have 2 to the power of x times 2 to the power of negative x. Product law says I can add those exponents. X plus negative x is actually 0. This is going to give me 2 to the power of 0. And over here, 2 to the power of x times 4, that can just stay. Okay, we can simplify this one step further. Anything to the power of 0 is 1. So we got 2 to the power of 2x minus 1 equals 2 to the power of x times 4. So now this is a quadratic equation in which the variable for the quadratic equation is actually 2 to the power of x. If we wanted to see this more clearly, we could still apply the power law again to this situation, in which case you'd be able to see, and I can rearrange this as well. But basically, if we applied the power law again, you would see that you have 2 to the power of x squared minus 1 equals 2 to the power of x to the power of 4.
What's different between that and the line above it?
All we did is separate this out so that you could see that the variable is 2 to the power of x, and there's an order of 2, an order of 1, and an order of 0. So now I'll rearrange it, and it'll be even easier to see after we rearrange it. We'll write it in standard form, a quadratic set equal to 0, where the variable is 2 to the power of x. So what do we have? We have 2 to the power of x squared minus 4 times, maybe I won't bracket the 4 anymore, 2 to the power of x minus 1 equals 0. What did we do there? we, I won't say rearranged, we wrote in standard form for quadratics. Okay, this is where you kind of take a break and say, what did we do? We saw that there were descending powers here, but we didn't want to work with a negative power. So we multiplied every term by the variable 2 to the power of x. Once we did that, we eliminated our negative exponent using the product law, and it ended up giving us, as we simplified it down, a quadratic where we had our variable squared minus 4 times the variable minus our constant, set it equal to 0. Now that we're in standard quadratic form, we should be able to pick a strategy for solving this thing. So right away you could think, okay, could I sum in product? In which case I'd be looking for two numbers that add to -4 and multiply to -1. That's not possible. The only options there would be +1, -1, and they certainly don't add to -4. So we're going to be using the quadratic formula here. There are two different ways to do it. Okay, you still have quite a bit of space on your page. If I were you, I'd maybe split the page down the middle. I'm going to scroll up. I don't think I'll be able to fit it in my space, so I'm actually going to erase what I have so far. Okay, after working with it so far, we have 2x squared minus 4 times 2 to the power of x minus 1 equals 0. And if we're going to be using the quadratic formula, we need our parameters a, b, c. A is 1. Okay, that's the coefficient in front of your starting term, your variable squared term. B is -4. C is -1. And by the way, this is method 1, so this is kind of on the left side of your page. And now we just plug in what we know. Well, our variable is 2 to the power of x, and we know it equals -b plus or minus square root of b squared minus 4ac over 2a. Negative b would be +4 plus or minus square root symbol. -4 squared is going to be 16. Skipping some steps here, hopefully you can keep up just fine. And minus 4ac, well, a and c are both 1, and I'm going to have two factors, two negative factors, so we're going to be adding there. We're going to be adding 4. All over 2a, which is just 2. If this is not helping you at all, you can write the quadratic formula up here, -b plus or minus square root of b squared minus 4ac over 2a. And now we're just working it out. And when we get to the end, we're going to be in a situation where we have 2 to the power of x is the solution that we're getting. We still need to figure out x after that. But here we go. We've got this radicand is 20, so you've got 4 plus or minus radical 20 over 2, and you should have some skills to reduce this thing. 20 can split out to 4 times 5, which means radical 4 times radical 5, which means the square root of 4 is 2, so you have 2 radical 5 here. So you've got 4 plus or minus 2 radical 5 all over 2. Which means that both of our terms in the numerator are divisible by 2, so I can eliminate that. We've got 2 plus or minus radical 5. Okay? If you really don't like that method, where we have 2 to the power of x, that's hard for you to visualize, you can do this. You can let k equal 2 to the power of x. And now what you get, or any letter, doesn't matter, just don't pick x. Now what you have is k squared minus 4k minus 1 equals 0. And from there, you can do the quadratic formula. You'd be doing it for k. K equals this. And then at the end, you'd get this exact thing. You'd get k equals 2 plus or minus square root of 5. And then you'd have to remember that actually k equals 2 to the power of x. So you'd still have to write 2 to the power of x equals 2 plus or minus radical 5. Okay, if that's helpful for you, if it's hard to visualize it as 2 to the power of x being your variable, then just sub in k for the time being, and make sure you sub it out again when you get to the bottom. Okay, this equation appears to give two possible solutions for 2 to the power of x, right? One where you add radical 5, one where you subtract radical 5. So we actually have to consider both of those cases. Case 1, let's do where we add radical 5. So in case 1, 2 to the power of x is equal to 2 plus radical 5. And I'll just draw case 2 over here, keeping in mind that these are now not connected. Yeah, it's not like case 2 extends from this side and case 1 extends from this side. Okay, this is just two ways to get this. And now we're on to something new, considering the two cases that present themselves from the solution. So this one would be 2 to the power of x is equal to 2 minus radical 5. Okay, I'm just going to whip through this because the strategy is similar to what you've seen before. We're going to take, because x is in the exponent, our variable is in the exponent, we don't like that, we're going to take the common log of both sides. When you're taking the log of the right-hand side, make sure you keep that whole right-hand side as a group. Why did we do this? Well, on the left-hand side, it allows us to move our variable to be a multiplier out in front. Right-hand side doesn't change. It's a weird value, but it is just a value. And then I can divide both sides by the log of 2, which gives me a final answer, a final exact answer of x equals the log of 2 plus radical 5 over the log of 2. And if we punch that into the calculator carefully, so again, you do as much work as you can with using exact values before you go for your calculator, because your calculator will give you a rounded answer. You end up with approximately 2.08. And that's the solution for this case. But the other case is where you subtract radical 5 from 2. Can you see any problems with that?
Well,
is any power of 2 going to result in a negative number? Because radical 5 is greater than 2. So this is actually a negative number. Yep. So notice that radical 5, let's do it this way. 2 minus radical 5 is negative.
So if there's quadratic as a function?
Okay, so if this side is negative, 2 to the power of x, the graph of 2 to the power of x looks something like this. It can never be negative. Okay? So there is no, we would say this root is extraneous. 2 to the power of x is never negative. Therefore, this root is extraneous, outside the realm of reality. So there's a single solution for our original equation. This guy was our original equation. Took a lot of work, but we got one solution for x, 2.08. And that is lesson 7.2. Extraneous roots. It's a possibility, so look out for them. It happens when you end up multiplying both sides of an equation by a non-constant factor. So we didn't multiply both sides by 2, that would be fine. We multiplied both sides by 2 to the power of x, which introduced the possibility of extraneous roots.